Welcome back, Doyle Crew. Today we've got an exciting new lesson on Redox Reactions. This is Mr. Doyle coming to you live this morning from a frosty, cold, snowy Lee Summit, Missouri. We are going to continue on where we left off yesterday on Redox Reactions. But first, if you go and hit that like and subscribe button, that'll really help me out. Going to get that subscriber count up so I can start giving some giveaways out. So, let's go on. So today's lesson on redox reactions, we got 4 types of chemical reactions, or really 5 that we've talked about before: synthesis, combustion, decomposition, and single and double replacements. And the one today on redox, which is short for oxidation reduction reactions, isn't like a brand new reaction. What it is a way of looking at old reactions through a new lens. So we got redox reactions, which are any reaction in which electrons are transferred from one substance to another. Okay, so we should already have that down. In our example here, we were burning magnesium. You guys have seen this before a couple times in class. But what's starting out over here as elemental magnesium and oxygen, both those have 0 overall charge, and something happens between reactant and product side where electrons are going to transfer from one substance to another. Magnesium is going to go from 0 charge to a +2 ion over here, and oxygen is going to go from a 0 charge on the left to a -2 charge over here. And that can only happen if electrons are moving around. Remember, we can't move protons. They're in the insides of atoms, so they're not going to react. And if you were able to do that, well, you're changing what the substance is. So you've got to move electrons around for redox. Okay, so each part of a redox reaction, the oxidation part and the reduction part, must happen for the overall reaction to occur. I can't have an oxidation reaction by itself. It's got to be partnered up with a reduction reaction immediately following, or this does not occur. So, what is oxidation? Well, that is the complete or partial loss of electrons from a reactant. Okay, so you are losing electrons. Okay, it's going to come back a lot. So try to remember which one's which oxidation is losing. And what that looks like if you were to put it in kind of an equation form here, sodium is losing an electron. Okay, it likes to lose electrons because it likes to form +1 charges. It loses that electron, so you see an arrow, and then the electron is off on the right here. Okay, and for each electron it loses, it gains 1 more in charge. Well, sodium likes to lose just 1, so it forms a +1 charge. But for this to happen, it doesn't just happen by itself. That electron's got to be picked up somewhere. It doesn't just sit around in free space. Okay, it's got to go somewhere. And based on what this is right here, it's going to be some kind of thing that likes to form an anion that's also going to get reduced. But it doesn't just happen by itself. Okay, this doesn't just occur with electrons just floating around freely. They've got to go somewhere. Okay, they're going to get picked up. And where they're going to get picked up is the reduction half of this reaction. Remember, I said just a moment ago, you can't have one without the other. You can't have oxidation without reduction. It's a redox reaction, so you got to have both. And reduction, then, opposite of oxidation, is the complete or partial gain of electrons. Okay, so it's gaining electrons. It's gaining negative charge. An example here, so this is elemental chlorine, Cl2. Okay, plus, and so each chlorine needs to gain 1 electron because they like to form -1 charges, so you would need to gain 2 total electrons here to make this work. But that Cl2 splits apart and we get 2 chloride ions is what happens there. Notice this time the electrons are on the reactant side, on the left side of the arrow, because we are adding them. They're gaining, okay, they're being combined with something, okay, that's going to get reduced. And then as far as how you remember which one is which, how do you remember which one is oxidation and which one is reduction? And I learned this when I was in probably 7th grade, and I know it sounds kind of almost like a 2nd grade acronym here, but I have never forgotten it since then. Leo Lion says GER, even though lions don't really say GER, but whatever. This has been the acronym that I've used to remember this. Leo, meaning losing electrons, is oxidation. Okay, so Leo, and GER, gaining electrons, is reduction. In fact, if you could just remember one of them, if you just remember that losing is oxidation, losing electrons is oxidation, then you should remember that gaining is reduction. So if you can just remember one of those two, honestly, you can figure out the other one. Another one that's often is used here is oil rig, uh, which is oxidation is losing, reduction is gaining. Whatever you need to do to remember these things, like I said, this is what I learned a long, long time ago. Even though it's kind of childish, it does get the point across, and hopefully you won't forget it. So all you have to do is remember one of them, because the other one is the exact opposite of that. Okay, so how do we tell what's actually gaining or losing electrons? Well, we have to look at oxidation numbers, or oxidation states. The definition here, the number assigned to an atom or ion to indicate its degree of oxidation or reduction. And there are rules for this on an upcoming slide that you're probably going to want to screenshot, because there's quite a few of them, so that way you can keep it handy. But there are rules to determine this, okay? In this example reaction right here, you have 2 potassium atoms reacting with Cl2, giving you 2 potassium chloride, okay? Throughout this reaction, potassium, each of them, loses 1 electron and has an oxidation number of +1. So by the time it arrives over here, it's gone from 0 to +1. And each chlorine, now there's 2 of them, gains 1 electron coming from the potassium, okay, and has an oxidation number of -1. So each one has gained 1 more electron and now has a charge and an oxidation number of -1. Charge and oxidation numbers can be similar, but they don't necessarily mean the same thing, and you're going to see some examples later on of that. But in any case, we have electrons moving around in this synthesis reaction. Okay, it's a new lens at looking at things we've already talked about. Okay, concepts. When an atom or ion is reduced, the oxidation number decreases. Okay, when it is reduced, the oxidation number goes down. Okay, and when you're oxidized, the oxidation number goes up. The charge goes up. All right, this hopefully kind of makes sense here, right? Reduction results in an oxidation number lower than what you started with, and oxidation results in an oxidation number larger than what you started with. Okay, so hopefully just the terms there alone can help you remember that. If you're getting reduced, your charge or oxidation number is going to go down. If you're getting oxidized, your charge or oxidation number goes up. And we're going to see examples of this. Like I said, there are some rules coming up here pretty soon to help us figure that out. Okay, so a couple more quick terms before we do that. Using that same reaction from a couple slides ago, potassium is oxidized by chlorine, by Cl2. We have to look at it in terms of something we call oxidizing and reducing agents. And you're like, well, what is that? Oxidizing agent, a substance that oxidizes another substance by accepting its electrons, and a reducing agent, a substance that reduces another substance by losing electrons. Okay, this is just a really fancy way, and a maybe long-worded way of saying an oxidizing agent. What that is the thing or species being reduced, and the reducing agent is really the thing being oxidized. Well, why the heck would we go through all this trouble to come up with another term here, right, for something like, well, if it's being reduced, why are we calling it the oxidizing agent? Isn't that backwards? What's going on here? Well, and the reason we call it that is because that substance, yes, it is being reduced, but it's the agent that allows oxidation to happen. And for another reason, why do we call it this? Well, that's because when we buy chemicals that are going to oxidize or reduce things, it doesn't say that on the side. What it says is strong oxidizing agent or strong reducing agent. That's what it tells us, so we have to be able to know what that means. Okay? So the oxidizing agent is really the thing being reduced. The reducing agent is really the thing being oxidized. Well, if we come back up here and look at this reaction, potassium goes from 0 as a charge here to +1, and chlorine, each of them is -1, or sorry, back in the reactants, they are 0, and then they go to -1 over here. Potassium is oxidized in this reaction. Well, how do we know that? Well, okay, in a moment here when we see the rules, it's going to go from 0 to +1. Its oxidation number went up, right? Okay, so it went up, went from 0 to +1, so it got oxidized. We also call it a reducing agent. It's the thing that allowed the chlorine to get reduced. Okay, so potassium is oxidized in this reaction, but we call it the reducing agent. Chlorine goes from 0 to -1 over here, okay, and it's reduced. Its oxidation number went from 0 to -1. It went down. We call it the oxidizing agent. So chlorine's a good oxidizing agent, even though it's the thing that gets reduced. So hopefully that's not too confusing for you, but that's what that means. If you see those terms, oxidizing agent, reducing agent, know that means the opposite thing. Okay, so what about if I'm looking at it from a reaction? If I've given a chemical equation here, can I figure it out? Well, again, in a moment here, you'll see all the rules for this, but basically elements by themselves have a oxidation number of 0, and ions have an oxidation number of, well, whatever the heck the ion is. So from reactant to product, we're looking at what's going up and what's going down. Well, it says which substance is being reduced. Which one had the charge go down? Well, here, iron went from +3 to 0, and the substance being reduced is actually that. Fe plus 3. The iron 3 ion there is the thing being reduced. Not iron. If you wrote just Fe, you'd be wrong because, well, over here it's already been reduced. Okay, by itself, Fe, that's already been reduced, but the substance being reduced is this. Which substance is being oxidized? Well, which one's charge went up? Well, we only have one other option here. Aluminum goes from 0 to +3. Okay, and which one of it is actually being oxidized? Well, the Al is being oxidized. If you wrote Al plus 3 here, you'd be wrong because that's already been oxidized. That has already happened. Okay? So identify the oxidizing and reducing agents. Well, remember, it's the opposite thing. So the substance being reduced here was the Fe plus 3 ion. So that means that's actually the oxidizing agent. And the reducing agent is really the thing being oxidized, and that would be aluminum in this example. So don't let that confuse you. That's all that means, right? It's going to be the opposite of whatever, okay, it's happening to it. Here are your rules. You should screenshot these. But basically what I'm going to do is just very quickly give you a rundown of them and explain what they are and the relevant parts to it. So number one, basically if you have an atom of an uncombined element, its oxidation number is 0. Okay, so sodium by itself with no charge is 0. Any of the diatomic elements by themselves are 0. Any element that's just the element is 0. If you have a monatomic ion, it's just equal to whatever the charge is. So like calcium plus 2 has an oxidation number of plus 2. Bromide with a -1 has a -1 oxidation number. The oxidation number of the more electronegative element in a molecule or complex ion is the same as the charge it would have if it were an ion. Don't worry about this too much because we haven't talked about electronegativity, but there'll be a way actually to figure this out without having to do anything else. The oxidation number of the most electronegative element, fluorine, is always -1. So fluorine is always -1 in compounds. Fluorides are -1. It has no other option. It's always -1, fluoride. The oxidation number of oxygen in compounds is always -2, except in peroxide, such as hydrogen peroxide, where it's -1. It is bonded to fluorine, the only element in the more electronegative than oxygen. The oxidation number of oxygen is positive. Look, we're not going to see this. I'm not going to deal with the second part of this. And if it's a peroxide, it's going to tell you that. It's going to be in the name of whatever it is that I'm giving you. You're not going to have to guess whether I've given you a peroxide or not. For the most part, assume that oxygen is -2, okay? And if it's a peroxide, I will tell you it would be -1. That's not going to be nearly as common, though. I mean, probably 99.9% of the problems I would give you are going to have oxygen as oxide with a -2. Or, I mean, in this case, it's not oxide, but it's in a molecule, so it would still have an oxidation number of -2. 6, the oxidation number of hydrogen in most compounds is +1, except in hydrides. All right, look, we're not going to see these either. I've never given you a hydride before. Those things are pretty dangerous, so we don't see that. Number 7, the oxidation number of group 1 and 2 metals and aluminum are positive and equal to their number of valence electrons. Pretty straightforward. Basically, group 1A elements +1. Okay, group 2A elements +2. Group 3A elements, well, for the most part, are +3. 8, the sum of the oxidation numbers in a neutral compound is 0. So, that helps us figure out if, like, there's one we don't know, say, for instance, like, well, what is this bromide here, or bromine, right? What's the oxidation number? Well, the overall one here is 0. Okay, the overall charge there is 0. So if we know one of them, that means we can figure out the other one. And we've kind of been doing a form of that all year long already. And lastly, the sum of the oxidation numbers of the atoms in a polyatomic ion is equal to the charge of the ion. Okay, so over here we have a sulfite ion, SO3, with a -2 charge. And it wants to know, well, what's the oxidation number on the sulfur? Well, we have a rule on oxygen. It's each -2. So that would be a total of -6. But instead of equaling 0 like I did before, it has to equal -2. Okay, so that means that the sulfur is in a +4 state. Okay, its oxidation number is +4 there. We're going to do examples of this. Don't worry if you're still not with me. Okay, so example here, what's the oxidation state of, well, actually I'm going to just cross that out because we know potassium already, because there's no way that we don't know that. The one that we don't know from this is chlorine. Okay, potassium is a 1A metal, so its oxidation number and charge is +1. Okay, oxygen, rule 5, is always -2 unless it is a peroxide or bonded to fluorine. This is not a peroxide. The name of that is potassium chlorate, so that's not a peroxide. So the question is, what's the chlorine's oxidation number here, right? And even though chlorine's a halogen and likes to form -1 as its charge, it's not its oxidation state in KClO3. Well, the sum of these have to add up to 0. I have 3 oxygens, each is -2. Okay, so that's going to be a total of -6 coming from that one. Okay, chlorine can be an X because we don't know that, and potassium is a +1, right? It's a 1A metal. So putting that all together, basically you have, right, X minus 5 equaling 0. So the oxidation state of chlorine in KClO3 must be +5. Okay, and that's going to be a very, very strong oxidizing agent because it likes to be reduced. It's at +5. Chlorine isn't really going to stick around at that. It's trying to get closer to 0 or -1. It's a little bit better off that way. So that's going to turn out to be a strong oxidizing agent because it likes to be reduced. Okay, taking a look at a single replacement reaction then. We have 2 potassium bromide plus chlorine gas. This is a single replacement where and actually I wrote this backwards for you, that's okay. The chlorine is going to replace the bromine, and the chlorine is above the bromine on your activity series, so that is going to occur. We get aqueous potassium chloride and liquid bromine. Well, let's identify the oxidizing and reducing agents here. Potassium in a compound, it's a 1A metal, so it should have a +1 charge. Well, the overall compound here must equal 0, since there's no charge to this whole thing. So that means that the bromine must be -1, right? I've only got one of them. Elemental chlorine, so element by itself, diatomic, has an oxidation number of 0. Okay, that's going to be the same case for this bromine over here on the right. It's going to have an oxidation number of 0. Coming back over here, the potassium is still +1. It's a 1A metal in a compound, so it's still +1, and the chlorine is now -1 as a chloride ion because it's got to equal 0. So, identify the oxidizing and reducing agents. Well, let's just first figure out what is being oxidized and what's being reduced. Remember the acronym from earlier? LEO, GER. Okay. The thing that is losing electrons is being oxidized. And if you're losing electrons, okay, means your charge or oxidation number is going up. So if we come back up here, well, potassium didn't change. It was +1 and stayed to +1, so it didn't do anything, so it's not being oxidized or reduced. Bromine goes from -1 to 0, So that qualifies as being the charge going up. Now, as far as exactly what is being oxidized, right, the potassium part of this has nothing to do with it. The part that actually is being oxidized here is just that. Okay, so the part that's actually being oxidized is a bromide ion. Okay, so if we're looking at GR, then for gaining electrons, it means you're gaining more negative charge, or your oxidation number is going to go down. Well, it can't be potassium because, well, it stayed the same. Chlorine goes from 0 to -1, okay, from left to right. So when it went down, that is going to be what's getting reduced, Cl2. Okay, that's the species getting reduced here. All right, well, as far as identifying the oxidizing agent, remember that's the thing getting reduced. Cl2 is your oxidizing agent. Your reducing agent is the thing being oxidized, and that's the bromide ion there. Okay, a couple more examples off of your homework this time to get you guys started. So, it says determine the oxidation number of the boldface element in these compounds and ions. All right, I'll do a couple from up top and maybe one of the ions down below. So, here HNO3, okay, there were rules on hydrogen, there were rules on oxygen, there were no rules on nitrogen. It is a compound, so the overall must equal 0. Okay, so we have to add up to 0. I have 3 oxygens. Each one is -2 from our rules, so that's a total of +6. Nitrogen can be the X here. And hydrogen, it's going to be +1. We don't have any instances where it's going to be -1. I've only got one of them. So again, we have x minus 5 equaling 0. X is equal to 5. So the oxidation number of nitrogen in the first one there is +5. Okay. If we come down to, let's try number 9. This time I have an ion, IO4, with a -1 overall charge. So instead of equaling 0, they're not going to add up to -1. Each oxygen is -2, and I have 4 of them. That gives me a total of -8. Okay, and I have 1 iodine, so it could be X. Well, basically then you have X minus 8 equaling -1, and we end up with X equals +7. Okay, this would be a per iodate ion there. But we end up with a +7 oxidation number there for the iodine. Basically, that's as high as we're going to see. There's not going to be anything bigger than that. ±7 is kind of our extremes there. But everything else is going to fall somewhere in the middle. Okay, so that should at least get you a few examples, a couple examples to get you through the first part there. Part 2, identify the species oxidized and the species reduced in each of these redox equations. So you're going to have to go through with the rules that hopefully you screenshotted, that I told you to screenshot, and you're going to apply the oxidation numbers. So bromine is going to have an oxidation number, so Br2 just by itself, elemental bromine, has an oxidation number of 0. Elemental gallium, element 31, by itself, no charge, oxidation number of 0. Okay, now we get over to the right side. We have 3 bromide ions. Don't let that try to confuse you. It's in a compound. It's just bromide. So each one of those is -1, right? And gallium is a 3A metal, so it's going to be +3. Okay, and if you're not remembering which one is oxidation and which one is reduction, use the acronym. That'll help you. Okay. All right. If I am losing electrons, my charge is going up. -1 is going to be +1. So, of the two things here, gallium or bromine, the one that has its charge going up here is the gallium. Okay, Ga. The thing getting reduced is the one that has its oxidation number go down. We're going from 0 on bromine to -1 as a bromide ion. The actual species being reduced here is the Br2, okay? Because if you wrote Br -1, you'd actually be telling me the product. Well, that's already been reduced, okay? All right, another example here, number 16. 2HCl plus Zn, giving us ZnCl2 plus H2. This is that reaction that actually generated the hydrogen gas when we were doing the hydrogen rockets, if you remember that. That's the things that we were adding together right here. So, in any case, anything that's an element we can already mark as 0. Zinc by itself is an element, H2 by itself is an element. And then we have two compounds that we kind of need to figure out what's going on with. Hydrogen in compounds is +1. Chlorine is going to be -1 then, because it's going to have to be, because overall has to be 0 on the compound. And then ZnCl2, well, each chlorine is -1 in a compound here as a halogen. And then the zinc then is going to be +2 to make that work. So what's going on, right? Which one is the oxidation? Which one is the reduction? Remember, oxidation is losing electrons. I wrote the acronym up there again just because need it, in case you need it. Oxidation is losing electrons. Which one had its number go up? Well, hydrogen goes down, chlorine stays the same, so the only option here is the zinc is the thing being oxidized. It's going from 0 to +2. And then what's being reduced? Well, the chlorine is going from -1 to -1, so that's not doing anything. The zinc is already being oxidized, so the hydrogen going from +1 to 0 is what's being reduced. Now, specifically here, the hydrogen in this compound is not H2, right? If you wrote H2 as being reduced, you're telling me that was reduced. Well, it's reduced over here, okay? This part over here is the one that's going to be reduced, or in the process of being reduced, and that is that hydrogen ion, H+, okay? All right, that part of it. The chlorine, if we separate them out here, is not doing anything. It's not a part of the reduction part of this. Okay, so hopefully that was helpful to you. Go ahead and try to complete the rest of that first worksheet, okay? Go ahead and smash that like and subscribe button if you haven't yet to get fresh chemistry content on a regular basis. As soon as I hit 100 subscribers, we'll have the next giveaway, so see you next time.